So we're going to look at model selection again. This is part one of regularization. It's going to introduce linear algebra, and it's going to do so as a means both of model selection and looking at multilinear regression. So let's look at multilinear regression. It starts with structured data, and the goal is a model y as a function of x1 to xn given the parameters beta 1 to beta k. And all of this data is numerical. In fact, the y here is associated with the entire real line, so infinitely many possible values for y. In other words, this is what we call a regression problem. So we're going to define F to be the n by n matrix of features. Again, these are all numbers. And Y, the sampled responses. And then multilinear regression says that to find the best parameters, beta, we minimize the Euclidean norm squared of F beta minus Y. Now, if we write that out as a summation, it looks like this. And we're looking for the argmin, the beta hat, which is the argmin of this sum of these things squared. The result is a model, f of x1 to xn, which is linear in the x1 to xn. For example, suppose we have linear plus noise. So I've generated a set of data from the line y equals 2x plus 3, and I've added a little bit of noise. So our data is the x's and the y's, and our model is beta 0 plus beta 1x. That's the equation of a line. What I'm going to do is I'm going to think of this as x0 to the 0th power and x to the 1st power, so that I can get polynomial features. The x0 is all 1s, and then the x to the 1st is just the original x's. And that means that my f here is the set of x's, the matrix of the x values, and the y is just the y values. So my f is of the form a column of 1s followed by the x's. Our betas is the beta 0, beta 1 in the model. And we want to solve for beta hat as the argmin of this sum of beta naught plus beta 1 xi minus y phi squared when we're summing over the data xi, yi. But that is the same as this expression, which is the same as multilinear regression. So here is the Python for that. So here is our linear regression, and not fitting the intercept because we're actually calculating the beta naught on our own. So the score here is 0.92, and that's the coefficient of determination. And it's 1 minus the total squared error, or the total sum of squares. So if its total squared error is very small, this is close to 1. And so this is kind of like a proportion, a correlation coefficient. So it's 1 is best, and anything less than 1 is progressively not good. So we got 0.921, not too bad. So the coefficient of determination as a formula looks like this. Closer to 1 is better. Here is our first beta. It's 2.92. In the original, y equals 2x plus 3, we have 3. And then beta 1 is 2.135 as compared to the slope of 2, the original line. And there we have our line of best fit. Let's do quadratic plus noise. So I've generated a quadratic data set with a little bit of noise. And here's my original data. And here's the model that I want to use. It's quadratic. So I need to put x to the 0, 1, and 2. And those are polynomial features. And now I have my matrix F. So sometimes called the data matrix or the design matrix in this case, because we're using polynomial features, and the y. And we have 3 betas, and we want to solve this problem, which is the same as multilinear regression. Here's the code, very much like what we did earlier. Coefficient determination 0.93, and here are our coefficients, and there is our quadratic of best fit. Let's look at the Moore-Penrose pseudo-inverse. For a matrix F, an n by n matrix, we define F dagger to be the argmin over the Frobenius norm squared, Fx minus the identity matrix, where for any A, the Frobenius norm squared is the trace of A transpose A. Sometimes the Frobenius norm is called the trace norm. Notice that we define this F dagger as an algorithm, a minimization of a quantity. So this is the Frobenius norm of matrix A squared, and F dagger is called the Moore-Penrose pseudo-inverse of F. For example, here's F. Here is its Moore-Penrose pseudo-inverse, the result of the algorithm. F dagger F is the identity, as we expected, and FF dagger is whatever the heck that is. There is some pattern there, however. And it's important. It's actually known as a projection. So if I'm going to do a multilinear regression, beta hat equals argmin over the betas of the Euclidean norm squared of f beta minus y, then you can prove that beta hat is f dagger times y, the pseudo-inverse times y. So the pseudo-inverse generalizes the concept of an inverse. So if this is f dagger and f as before, then if I was to take f times 1, 1 and get 3, 7, 11, 15, then f dagger times 3, 7, 11, and 15 would give me 1, 1. Again, generalizing the concept of an inverse. So for example, in our quadratic plus noise, this parameter matrix 2.776, 3.05, negative 0.916 is actually f dagger, the pseudo-inverse of f times y. But typically in data science, we only get the data. We're not even told what the model should look like. Instead, we use what's called feature engineering to discover the form of the model as we fit it to the data. So for example, polynomial features. Given structured data, y sub I is sampled responses, a feature is a function. So in a more sophisticated context, we could say we never observe the internal state of anything. We only see functions from the internal state to our perspective, and those are observations or measurements. So in particular, the ith observation of the jth feature is just f sub j of xi. So here we have our features, and they're all functions applied to some underlying state, and then we have this response y. And those define our matrices for multilinear regression. A good example is when the features are functions that are defined by powers of the individual x variables. They're called polynomial features. We've seen them already. So we created new features like powers x to the 0 and x squared. So suppose we have data but no model, and we have the x and the y. Well, for good reason sometimes we can assume our model is a polynomial, and if we do that, then we can create polynomial features. We'll get our f from the polynomial features and our y, and then we'll find the argmin of the f beta minus y Euclidean norm squared, and that will give us our best parameter values and our solution, therefore, to our multilinear regression problem. But how do we choose D? Every model is a special case of a higher degree model. The linear model is a special case of the quadratic model, which is a special case of the cubic model, and so on and so forth. The degree d minus 1 model is a special case of the degree d model. What does that mean? That means that if I use this F1 as my feature matrix, then it's a submatrix of F2, and so on and so forth, of all submatrices of FD. The coefficient of determination, well, notice its value is determined by the numerator of the fraction. And notice that because the quadratic contains the linear as a special case, when I use F1, I get a bigger error than when I do F2. Therefore, the quadratic will be a better fit than the linear, always. And the cubic will be a better fit than the quadratic, always. And that continues indefinitely. The best fit is going to be when we use all of the features. But is that the best model? So, duality to the rescue. Suppose we have our structured data of this form. F is the features and Y is the responses. Multilinear regression looks like this, but it also looks like that. And the significant thing there is that I'm using weight notation for parameters, by the way. The significant thing there is this is the exponent of a Gibbs form inside the summation, which means that this mean squared error kernel in a exponent of a Gibbs form says we're minimizing a likelihood function. And if we're minimizing a likelihood function, then we're necessarily minimizing a cross entropy function. So let's rethink this in terms of entropy and cross entropy. So given our independent trials, we're going to look for P true. This is the true probability distribution of Y, the one that includes everything in the universe that can influence the distribution of Y, not something we'll ever know, but something out there that's generating our trials. In function notation, we've been working with vectors for our probability distributions, and now we're writing in function notation, and that just simply means that P true of Y is the Yth coefficient of the P true vector. Our empirical distribution, I'm also going to write in terms of Y, and that's the count of the number of times that we get T sub Y in M trials. That's our empirical distribution. By the law of large numbers with probability 1, the empirical converges to the true. Suppose also we have models with an increasing number of parameters. The first with 1 parameter, the second with 2, the third with 3. So these are parameterized models. And again, we're going to use the function notation, P of Y, given the parameters beta 1 to beta k, and that's the Yth coefficient of the parameterized vector. Here's our question. As estimates of the true distribution, how does P of Y, beta 1 up to beta k minus 1, compare to P of Y, beta 1 up to beta k minus 1, beta sub k, especially if the first one is a special case of the second one. In other words, for some value of beta sub k, I get identically the first one. So notice that because there are more parameters, we always will have a better fit from the model with more parameters because it includes the first one as a special case. Well, the answer to that question is via cross entropy. So here is our cross entropy, and notice that our cross entropy of the empirical with respect to the true is given by this. And if we look at the definition of cross entropy, then we can take the P true and divide by a model P and multiply by a model P, but then by our properties of logarithms, we can take that model P out on its own. So we have this first term minus the sum y equals 1 r, the empirical distribution of y log of the model. And that is cross entropy. So we have this first term plus cross entropy of the empirical with respect to the model. So the first term is called bias. And notice that the true entropy is approximately the cross entropy of the empirical with respect to the true, because as m goes to infinity, the empirical converges to the true. And therefore, the true entropy is approximately the bias plus the cross entropy of the empirical with this model. And that cross entropy is a log likelihood. So this leads us to what's known as the Akaike information criterion. So in 1973, he proved that the bias approaches k as m goes to infinity. In other words, that the true entropy of the true distribution, or the entropy of the true distribution, is approximately the bias minus the log of the maximum likelihood, or k minus log L star. This is where the log of L star, it denotes the maximum log likelihood. So the AIC criterion is defined 2k minus 2 log L star. For reasons that are not important, we like to put the 2 in there. So the AIC is the information lost in using this candidate model with the beta parameters up to beta k. The smaller the AIC, the less information lost, therefore the better the model, as long as the m is sufficiently large, because remember the empirical has to converge to the true. Given two models, the preferred model is the one with the smaller AIC. For example, our linear plus noise, we have this data, and let's suppose we fit it both with the linear and the quadratic. Here is the Python for doing that. The first part generates the data, noisy 2x plus 3, and then we get our polynomial features. And then we look at stats models, and we do ordinary least squares, the multilinear regression of y with this quadratic, and we can get a summary once we've done a fit for the linear, and we can do the same for the quadratic, and then we can compare. So here's what the comparison tells us. The linear model looks like this, and the quadratic model looks like that. Notice the coefficients are very different, so it's not a question of, they're close in some sense. The linear, of course, has a mean squared error that's bigger than the quadratic mean squared error. It has an r squared and a coefficient of determination, which is less than the quadratic. In other words, more parameters gave us a better fit. However, the AIC is smaller for the linear than it is for the quadratic. Remember, we just took 2x plus 3 and added noise, so we would think the linear would be the better model. And the AIC tells us that is exactly the case. So that brings us to model selection again. We've already seen the binary classifier. We can use precision recall or the ROC-AUC sometimes. And now we can also use the AIC, information criterion. Regression, we very often use AIC to compare models. And there are variations on all of these. BIC is Bayesian information criterion. And there's AIC little c, and so on and so forth. There are also variations on the confusion matrix-based metrics. But equally important is another issue, which is our next video. So we have all this data but no model. Given this big, huge assumption of this massive polynomial, do we create all the D models and then select one with the best AIC? No, it's not a good approach. Why? Because this is maximum entropy with constraints. And we want to find the best model by constraining the parameters. And that is the next video. Now, I'm going to conclude with just a quick look at the proof of the AIC, just a few more details for those interested. So it turns out what you actually do is you take the negative log likelihood and you expand it in a Taylor series of this form. The derivative term goes to 0 at the maximum likelihood argmin, and negative j is what's known as the Hessian matrix. Now, you'll have to combine this with what we did earlier, but when you put all this in, what you find out is that you get something that looks like this, and you've got your biased estimate, and you've got your bias with the Hessian term. It turns out that's essentially biased by the number of parameters, because there's a thing called the Hessian matrix, and it's very chi-square-like as m goes to infinity. And so that allows us to come up with the AIC if we wanted to do a rigorous proof. Just wanted to mention that in case you wanted more detail.